Hi, my name is Mads Smed, and this is our presentation of our paper, A Study of Extensive LoRaWAN Downlink Communication in a Mobility Scenario. This work is done together with Kasper Winkler, Davide Magrin, and Michele Albano. And thank you for tuning in to this pre-recorded version of the presentation. So, in this paper, we studied a low-power wide area network called LoRaWAN, which is a LPWAN which offers, as many other LPWANs, a long range of communication with little power consumption, but at the cost of a limited bandwidth. Most of the LPWANs are asymmetric, and so is LoRaWAN, where we consider more uplink communication rather than downlink communication. And in terms of LoRaWAN, it supports three classes of communication: Class A, Class B, and Class C, where Class A is mainly used for uplink communication, meaning communication from the low powered, sometimes battery powered end devices, which send, for example, sensory data from the world to the gateways. And then we have Class C, which is mainly used for downlink communication. This is the gateway or the hub sending packets down to the end devices. And then we have in the middle, we have Class B, which is mainly for uplink communication, but schedules fixed times where we can receive packets at the end devices. So the motivation for this paper is that we wanted to evaluate the feasibility of extensive downlink communication. And not just downlink communication, but downlink communication while we have end device moving around in an area. And we also wanted to study how to enhance the current approaches to deliver a large quantity of data to the end devices. For example, if we want to do firmware updates over the air, this could, for example, be if we have some old end device that we need to do a security patch for. Yes, so if we consider this scenario, this scenario we refer to as the mobility scenario, where we have, for example, in this case, a setup of 4 gateways. Each of them are sending or receiving packets from some end device, or sending packets to some end device. What we want to consider is the ability for end devices to move from within range of one gateway to another, or from within range of a gateway and out of the range. So in this case, we have an end device here moving from within range of gateway 1 to within range of gateway 3. So in terms of LoRaWAN, as I said, it's a low power wide area network protocol, and it defines 3 classes, A, B, and C, for end device operation. And the end devices can are able to switch between the classes. The main class of LoRaWAN end devices are Class A, but what we are interested in when we are talking about the mobility scenario and being able to send extensive amount of downlink communication, we are interested in the Class C, which stands for continuous listening mode, because in this class we are able to receive more packets. So in the typical LoRaWAN setup, we of course have the end devices, which are typically low-powered, battery-powered end devices, which sends, in some cases, sensory data from the world to the gateways via LoRaWAN. The gateways are able to send and receive packets to and from the end devices, and can modulate sort of different spreading factors in terms of the needs from the end devices. And here the spreading factors go from 7 to 12. So 12 is the highest, which has the longest range, but also the sort of the lowest bandwidth. And then we have the spreading factor 7, which has the lowest range but the highest bandwidth. So we need, like, the gateways usually able to do what we call adaptive data rate, so we can, in terms of the signal strength that we get from the end devices, being able to adapt the data rate accordingly. And then typically we have some kind of network server that controls the gateways communicating via IP. And to be able to control the network server, we usually have some application or create some application that control the network server to be able to schedule packets and so on. So in terms of the Class C for LoRaWAN, typically in Class A, normally we have a transmission window where we are able to transmit packets to the gateways or to the network, and we open up two specific receive windows at specific times with a specific interval. But for Class C, we want to be able to always receive packets whenever we are not transmitting. So in Class C, and per the LoRaWAN specification, we open additional receive windows. Yes, and to be able to sort of simulate LoRa networks, we use Network Simulator 3, or NS3 for short, which is an open source discrete network simulator which provides models for simulations of different packet data technologies, and provides sort of a general simulation engine. And in NS3, there's a big community that provides different modules for different technologies, so different simulation modules in what they call the NS3 App Store. And in our case, we use the already implemented LoRaWAN NS3 module, which currently only provides us with Class A end devices. So some of the related works to ours is some authors study mitigating packet loss when we are talking about downlink communication in Class A. Which sort of looked at what kind of approaches can we do when we wanted to avoid packet loss when we're doing a lot of downlink communication in Class A. For that. Then some others authors study the gateway selection if we are in a multi-gateway scenario. So what gateways should send to what end devices. And in this case, the result is that we should split the load between the gateways. And other authors also discussed the requirements for the firmware updates over the air scenario. More specifically, they discussed the requirements for effective firmware updates. But in none of the cases they're considered anything about mobility of the end device, meaning the reference scenario that we talk about, where we have either end devices going out of range or going from within range of one gateway to another gateway. So the main contribution of this paper is developing an NS3 module to simulate communication for LoRaWAN Class C devices, to be able to do simulation results with Class C instead of only Class A. And with that, a suitable propagation loss model for non-line of sight propagation, or NLOS, in LoRaWAN, which we base on a physical reference application, some physical experimental data. And then we showcase this new module by proposing and evaluating two strategies that we try out in a real world scenario, and then do some simulations to evaluate them. Yes. So for the rest of this presentation, I will first talk about our real world data collection, and then I'm going to talk about some of the simulation results of LoRaWAN Class C. So in terms of the real-world data collection setup, we have a sort of straightforward setup with two gateways, multi-tech conduits with LoRaWAN, and then we have some embed OS boards, more specifically the LoRaWAN discovery boards, as we use as end devices. And on the end devices, we install a simple base application that, one, are able to join the network whenever we power it on. It will join our LoRaWAN network. And then when the end device is powered up, and connected, we send an uplink message to the gateway and the network server to be able to configure adaptive data rate. And once we have an optimal connectivity setting, we switch to class C and are ready to receive an update. The network server we use is the ChirpStack network server, which provides a lot of features for different gateway settings, different the ability to make the gateways know that now they should switch in terms of where the end devices are and stuff like that. And the application is written in Python, which communicates with via the network server API to be able to schedule packets and so on. And for the scenario, it's featured in a urban environment which are populated with a lot of buildings here in Aalborg. And as you can see here on the map, we have placed the two gateways apart in two different buildings, and sort of this reference scenario should simulate, for example, a bike messenger cycling about in the city. And as you can see, the area is so densely populated that we actually have a dead zone in the middle. So we are at some point going out of range of both of the gateways. Yes. So to be able to combat this, we test out two simple strategies. One is what we call the out of signal strategy, where whenever an end device is about to be out of range, based on the received signal strength indicator, we will send a uplink message to the gateway saying, now we are about to be out of range. And then the other strategy is what we call periodic acknowledgement, where we at some fixed point send periodic acknowledgement on the downlink messages that we get, to be able to signal to the gateways that we are still here, or we are out of range and stuff like that. And then we actually also consider a third strategy, but this strategy we only consider in simulation. So the result of the out of range scenario, we tested out different signal strength, received signal strength indicator values of minus 140, 130, and 120, and we can see that because we are so densely populated with buildings in this area, we are not able to get sort of the optimal RSSI values. So here we get a lot of packet loss with this strategy, because we are not able to actually send the out of signal message. But if we consider the RSSI value of minus 120, we are actually able to, at this threshold, keep the packet losses at a minimum of 7% or 6.9%. So in terms of the other scenario, where we looked at the periodic acknowledgement, where we send a confirmed message or acknowledgement every sort of third, sixth, or ninth packet, we can see here that if we send acknowledgements too often, because we cannot receive any packets while we are transmitting, we are actually getting a high sort of packet loss percentage because of this. And the best result that we got is if we send every ninth packet, we get a packet loss of around 15% in this scenario. So to also do some simulations with the Class C devices, we have implemented a Class C component in NS3 on top of the currently implemented LoRaWAN module in NS3. And with this, we have simulated the experimental scenario by using the GPS locations of the gateways and the different experiments that we did, and then we were able to tune a propagation loss model, more specifically a log distance path loss model, to fit with the experimental data. And to do so, we have set the path loss distance exponent to 4, and with a reference path loss of 60 dB at 2 meters. And the results that we got is actually quite good. We are able to match the experimental data quite well. As you can see here on this graph, on the y-axis, we have the received signal strength indicator in dB, and we can see that we are able to match it with the experimental data. Yes, and with this fitted or tuned loss model, path loss model, we are able to do some more experiments with the different placements of gateways now that we are able to simulate based on this. So what if we consider sort of the gateway placements that are best for our firmware update scenario while we are considering moving end devices? So we looked at two different scenarios. One where we placed the gateways randomly, and one where we placed them in a grid formation. And on the left, we have the random placement, and this sort of corresponds to the real world scenario. For example, if we consider the Things network, crowdsourced gateways that people put up, they correspond more to sort of a random pattern compared to a grid or fixed gateway deployment like this. And the rings, as you can see here, correspond to the different spreading factors. So the lowest spreading factor, which has the fastest data rate, is this one, and the highest spreading factor with the lowest bandwidth is this one. So we can see the range of the gateways. We can see that if we compare the random placement of gateways to the grid placement, we can see that the grid placement actually outperforms, as expected, the random placement. And in this graph, we can see that the proportion of end devices updated compared over time. We can look at the empirical cumulative distribution function for this, and we can see that in all cases except for one gateway, we actually outperform with the grid placement. And we use the bulk strategy, which is the strategy where we don't send any uplink from the end devices, and we are only doing downlink, and the gateways are active at all time. We can also look at the and simulate the different policies or the different strategies we come up with. And we can see here that on the left, if we look at the different strategies, the out of signal, periodic, and bulk, we can see that, of course, the bulk compared to the other strategies outperforms, and we can actually see that when we do our simulations, we can actually see that our in terms of the cumulative distribution function here, we can actually see that the periodic performs a bit better in terms of updating end devices. On the right here, we take a look at the bulk scenario, or the bulk strategy, where we look at the bulk strategy with different spreading factors. So again, we have the proportion of end devices updated over time, and we can actually see that there's actually a payoff for not doing the lowest spreading factor, because when we have the lowest spreading factor, we also have the lowest range, and when end devices are moving, the chance of moving out of range of a gateway is a lot bigger. So we actually get a better result having a bit higher spreading factor. To conclude on this work, we developed a Class C NS3 component, and we tested the two strategies for communicating signal strength to the gateways, both in the physical environment and in simulation, and it showed that the choice of strategy greatly impacts the packet loss in terms of the mobility scenario. So some of the sort of near future works or the future works for this work is that we should consider more complex strategies for the mobility scenario, and we should also do more physical experiments to maybe fit an even better model. We should also investigate the system's behavior when we scale it to hundreds of end devices and see how the system reacts. We should definitely, in terms of simulation, implement Class B in LoRaWAN NS3 module to be able to figure out when should we use Class B compared to Class C. And then it would be ideal to expand the network server implementation in NS3 to accommodate installing applications to experiment with other sort of gateway strategies and not only end devices. Yes, and that concludes my presentation of this paper. Do you have any questions?